So we've found our Lagrangian or our Hamiltonian and we've got our equations of motion. Let's tackle the problem of solving the equations of motion. In general, what we're dealing with here are systems of coupled differential equations. So what are our options for solving those? Well, if we're lucky, we'll recognize the equations, in which case we'll know the solution. If we're a little less lucky, then we might find them in a book or in some kind of table. If we're a little less lucky again, we might have to go to a Russian to find the analytic solution. And if we're less lucky again, then we're going to have to resort to numerical methods. In fact, these days, the modern physicist tends to use computers to do the analytic parts of their work as well as the numerical parts of their work. One of the reasons for that is that it's just more efficient in some cases, and you're less likely to make mistakes if you have a well-debugged system. It's very easy to not make a mistake over 2 lines of algebra. By the time you're doing, say, 300 lines of algebra, the chances of you not making a mistake get vanishingly small. And so you need other methods of ensuring that you're doing the right thing. So using computers is a vital part of solving any dynamical system and really understanding what they're doing, and also in the visualization process. Because you're going to be doing the detailed analysis of a dynamic system for your project, we're going to have a look now at one method, and you can use whichever method you like when you go to do it, but we're going to look at one method using one package, the Mathematica package, for visualizing equations or the behavior of equations, for solving them, and for understanding them. If you're completely unfamiliar with Mathematica, if you've never used it before and you haven't done it in a previous course, then there are some resources, some links to good getting started tutorials that are linked to in the accompanying material with this lecture. So just to reiterate, although I'm showing you how to do things using Mathematica, feel very free in your world to use anything you wish. The point of using Mathematica is that I can show you how various bits of algebra and calculus are done in a symbolic sense, as well as the numerics, as well as the visualization. So that's why we make it available. But each of these things have equivalent packages that can do that in other places, and some of them are free. So by all means, practice with them. But if you'd like to use Mathematica, this template that I'm showing you now is attached to the lectures, so you can have a look at that anytime, and I'll walk you through how it works and why we do these things these ways. And in fact, as we go down, we'll also be talking a little bit about dynamical systems and how they behave. So the first thing to execute is this thing up here. This is just lets us talk about equalities, like this list of equalities here, where we've got a set of equations as lists. Okay, so our vector is going to be composed of x, y, and z, all of time, explicit functions of time, and I can solve that. So I can solve here, what if my acceleration is equal to a bunch of constant accelerations, my velocity has some initial velocities, and my initial positions are initial positions. So Mathematica is clever enough to solve that, as is any high school student, and we see the rather familiar form. Now, actually that looks a bit weird, the way it's got x of t mapping to this. So this arrow means x of t is going to map to this thing, y of t is going to map to that thing. Why is it putting things like that? Well, also, in fact, you'll notice it's in 2 sets of curly brackets. So one thing we can do is say, let's just take the first element of that. So we're making solution equal to the first element of that. And we've got rid of one of the sets of curly brackets, but we still have this list of replacement rules. So it's a list of replacement rules rather than a list of solutions. And there are some good reasons for doing that. And we'll discuss that after we explain just what a replacement rule is. So if I say x cubed, and if I type that into Mathematica, I'll get x cubed. If I say x cubed, and I use this symbol here, this means basically replace x with x plus a. So if I do that, I get x plus a all cubed, as you'd expect. If I had instead said x equals x plus a, then forevermore, whenever I got x, it would spit out x plus a. And indeed, that was recursive, so bad things would happen. Or if I'd said this, such that x equals x plus a, then this thing would forevermore be set to x plus a all cubed. So in order to use this list up here, what we can do is we just use this as a list of replacement rules, and I can say, what's x of t given this list of replacement rules? And it says, all right, well, I'll replace x of t with this, and so it returns that. And we can see that it does. There we go. In sort of high school, we learnt these exact equations. You might have used different things though. So let's replace a of x with a, vx with u, and x naught will start at the origin, and you get your more sort of recognizable x equals ut plus a half at squared, which you can get if you expand that. So it took out a factor of half in an attempt to make things easier, but I recognize it better as ut plus a half at squared. So now the key question is, why would you use replacement rules? And the answer is, when you use replacement rules, they don't change all the numbers. This happens time and time again in people's projects, so I really want to emphasize this. When you are doing your algebra, leave your variables as variables. Only put numbers in when you're trying to do numerics. And then if I have a formula like that, and I say g equals 10 to the minus 11, or whatever it's supposed to be, 6.67 by 10 to the minus 11 or something, then forevermore, wherever I used to have a big G, I'll now have a number. What's wrong with that? What's wrong with that is that if I have a whole bunch of numbers multiplied together, I can no longer check units. Okay, I can no longer check for reasonableness, I can no longer check limits. If I want numbers, I only really want them when I'm doing a picture. Otherwise, I want to see the algebra, and that's really important. It may not be important for really simple problems, and when you're in high school or in early years of uni, you've only really done very simple problems. But as they get more and more complicated, you really want to follow these rules. So if I want to get numbers for this, I map G to a number, I map M1 to a number, I map M2 to another number, and I map the distance between R1 and R2. R1 goes to R2 plus a number. And then it all comes out to a number. But then if I do this again, so if I do this, I get my number, but I haven't changed what these symbols mean. I haven't changed what G, M1, and R1 and R2 mean. And that's really handy. So that's why we do that. Okay, let's do some actual physics. This is old physics, physics we used to be able to do a long time ago. We'll use Hamiltonian mechanics, but we shouldn't see any surprises in the solution. So this is a one-dimensional harmonic oscillator, by which I mean it's just a normal kinetic energy term in the Hamiltonian plus a normal potential energy, which is quadratic in x. And you can write that out. So bam, I have my Hamiltonian. One of the nice things about Mathematica is that it knows how to take the derivatives of things. So if I say, hey, take the derivative with respect to px, and that'll be my r dash, and take the derivative with respect to x and throw in a minus sign, and that'll be my derivative with respect to px, then I get my equations of motion, exactly as I hoped. And so it's done the calculus for me. So as long as I got the Hamiltonian right, and remember to put in my minus sign, I have the right equations of motion. And now I can solve that in the normal way, so I'll plug in the same solution kind of command that I had before with my initial condition of x0 and p0 for my x and my p, and I get these two solutions. They're basically just cosines and sines with my initial values in there. If I want to plot it, I have to put in numbers. So here are my numbers, and you can see there it is. I get a beautiful circle. What's the circle mean? It means I start initially, my x-axis is my x of t and my y-axis is momentum. So initially it starts with 1, so it starts there, and 0 momentum. So it starts there, and it's just going around. So when it's up there, it'll start falling down, so it falls backwards, goes past the middle at speed, comes to a stop on the other side, and then accelerates back. And it just goes round and round and round. So going round and round and round in this phase diagram is the same as just rolling backwards and forwards in the quadratic potential. That's all very good. If I wanted to try different numbers now, then I would have to go up here into my replacement rules and type in different numbers, and it would work. Note that wouldn't have worked if I'd set m equal to 1, because then on all these other equations wouldn't have m's in anymore. So by using my replacement rules, I can just change these numbers and I get different answers. Often, however, I want to play more. Now Mathematica has a nice method of doing that. So if we go up here, we've got the function manipulate that lets us play. We clear our solution, we set up our solution, and we wrap manipulate around our plot. And here we go. So this slider here just says how far my time is going. So you can see that I've got a slider Tmax starts at 2, but it can go anywhere from 0 up to 10. And so I'm going 0 up to 10. And you'll note I've got locator and locator there. That means that as I click here, I get different initial conditions. So you can see that I'm just going round and round and round in a circle wherever I start. So if I start down here, I'm just going around in a tiny circle. If I start out here, I'm going around in a very big circle. Simple. That's what the harmonic oscillator does in phase space. And now we've got a good feel. And you can see that this locator method lets us rapidly figure out exactly what this thing is doing. You'll note that no matter where I start, it's getting the same length round in the same amount of time. which is in fact a property of the harmonic oscillator. Whether you do big swings or small swings, you get back there in the same amount of time.